Good afternoon. Good afternoon, everyone. Still, participants are joining. We'll have one more minute. Wait for one more minute, and then we'll begin the session. I request you to mute your mics. Fine. Fine. Can you please mute your mics? And again, good afternoon, everyone. Thank you all for your interest and participation in today's session. And today's topic is very important and mostly fundamental in nature. So, one for medical physics. It's like Monte Carlo radiation transport and regarding the photon interaction specifically. And this particular session is specifically curated for students and medical physics residents. And yeah, those are interested in our Monte Carlo simulation also. It will be very useful for them, interesting for them also. And we are pleased to have Dr. Bilal Hussain with us today. And he brings nearly 3 decades of clinical experience and more than 20 years experience in coding and teaching and mentoring students like MD, MBBS, and DNB students. And over this year, he worked on the design and development of radiotherapy information system, and he has designed his own simulation system, which is based on Raspberry Pi to do the all trillion kind of a simulations and all. Okay, and we sincerely thank Dr. Bilal Hussain for joining us today and share his valuable knowledge and experience going to be with us today. And now I would like to hand over the session to Dr. Bilal Hussain. Sir, please share your screen and please take over the session.
Thank you, Dinesh, for inviting me for delivering this lecture. So, as from the beginning, I want to tell that this session is like Dinesh has said, that this session is basically meant for the students, interns, and the very juniors who want to learn a little bit of Monte Carlo, especially the EGSnrc. So I'll be specially interested in EGSnrc. So only for that. So for the seniors who are already there in the session, so just bear with me and let me start the session now. Is everyone able to see the presentation, PPT PowerPoint presentation?
Yes, sir, it's clear.
Okay. So my name is Bilal. This is my second lecture in this Medical Physics Coding and Learning Hub. So earlier I gave an overview, an introduction to the Monte Carlo, especially EGSnrc. And this time I thought that we should talk a little more about the physics of Monte Carlo radiation transport. And especially today I'll be covering the photon interactions. Electron interaction, we'll cover it some other time. But this today's session, I'm going to cover about the photon interactions and some background about the physics. I expect that everybody is a physicist here, or at least studying physics here. So we know about the interaction of radiation with matter. So I'm not going to give you a very basic core interaction part. I'm going to give what is necessary for the Monte Carlo radiation transport. That I'm going to cover it today. So first of all, we know that a Monte Carlo is basically a probabilistic model or the system. It's a stochastic method for estimating the deterministic quantities. So which are deterministic quantities like dose, kerma, and so many things, but that are very difficult to or impossible to compute exactly or analytically. So we are using computational algorithms to evaluate these quantities. They are often used in physical and mathematical problems. Apart from the medical physics, they are also used in various other fields, like we have a nowadays stock exchange and also the weather reporting. All the places Monte Carlo is being used. Two important things actually I want to tell before going into actual physics. The whole of the Monte Carlo system is a stochastic method that is based on the probability model. So we have to sample from the probability distributions. Examples of probability models are tossing a coin, rolling a dice, and so many other type of examples can be given for this probability distributions. So I said that there are two important backbones for this Monte Carlo system. One of the backbone is the random number generators. Without a random number generator, no radiation transport can be modeled in a Monte Carlo system. So this is a major backbone of a Monte Carlo system, a random number generators. Though we know that a two random number generator is very difficult to get. We can't get a two random number generators. So we have to rely on the pseudo random number generators or sequences of random numbers which seems to be random. Like that's what I said, that when we say that they are not exactly true, it means that there should be a pseudo random sequence to appear random enough. It means that for as long as we are doing it, the number should not be repeated again and again. That's the thing. That's what we mean here by it should be random enough. Some of the examples of random numbers are like this: just before needle problem, like throwing a needle and finding out the area, how many numbers are falling within the line or outside the line, and also estimation of pi. These are two classical examples of random number generators being used in Monte Carlo systems. In our Monte Carlo system, useful for medical physics purposes, we have to use a different type of random number generators. So random number generators are nothing but an algorithm for generating a sequence of numbers that approximates the properties of random numbers. So random number generators basically produce a set of random numbers in a range of 0 and 1. So we have to always put that the random number generator is given by the epsilon symbol. The epsilon within a bracket we say 0 and 1. It means that the random number, this generator is going to generate a number within 0 and 1. And the problem with the pseudo random number generator is that it's got a period and execution time. Every generator requires a set of a period, means that after so many numbers, it will again repeat. Maybe if the number after which it repeats is very long, then I can say that it is a true random number generator. It's almost like that. But if the repetition period is very, very low, it means that within my simulation itself, the numbers will be repeated again and again. So that should be avoided. So we have already I have a inbuilt random number generators in many of the softwares available nowadays. Excel has got random function. Python has got a random module that I'm going to use actually extensively. I will be using it in today's lecture also. And also we have a LCG, linear congruential generators available. But the EGSnrc uses these random number generators like RANMER, RANCU, RANLEX, and RANLEX++. They have a very long periods. It means that almost during the whole execution of the Monte Carlo simulation, the numbers are not going to repeat again. The second backbone, first backbone was the random number generator. The second backbone of the Monte Carlo simulation is sampling methods. What is the sampling method? So how we are going to sample the things. This is again a probability distribution. I'm going to sample something from that. There are various sampling methods available in probability theory. Some of the examples are uniform sampling, inverse transform sampling, stratified sampling, acceptance rejection sampling, and there are so many others. We'll be using a couple of these sampling methods in my examples today also. These two forms a very basic backbone. One is the random number generator sampling method. So how we choose, which one we choose, that's going to give you the accuracy in a Monte Carlo system. Okay. So before going into actual physics part of that, I want to give you actually from where we can get the physics data. The physics data is already curated or made available by many agencies. One of the agencies is the NIST, National Institute of Standards and Technology. They have maintained a web-based databases. They have a X-rays and gamma ray attenuation coefficient calculation composition we call XCOM, commonly known as XCOM. XCOM data is very well known in the physics field and they are available. It calculates photon cross sections and the attenuation coefficients for elements, compounds, and mixtures less than, that means from 1 to almost 99 or 100. 1 to 100 atomic number material is already available, from which you can calculate for any mixtures also. I'll give you the example, like I'll show you the examples also. It covers energies from 1 keV to 100 GeV. XCOM photon cross-section databases are included and integrated into this data is already integrated into many of the MC codes, Monte Carlo codes available like EGSnrc, GANT, and many other things. They are already incorporated into that. I'll show you the raw data, how it looks like, and how to use that. That also I'll show you. The XCOM databases are commonly used in EGSnrc. Today I will be seeing one of the code I will be showing the demonstrations. Now I want to move on to the actual XCOM data, how it looks like. This is the XCOM directory. This is a web-based database available. If you go into database, we can see that it got a database search form. Upon clicking the search form, it will open a window where I can go for various elements. We have to say, suppose for example, I want to see the data of an element, then I want to get this one. Now we have to enter the either atomic number or the symbol. Let us say, for example, I want to go for a 74, which is the tungsten one. I just want to give an example. I want to get the attenuation coefficients, coherent, incoherent, photoelectric, pair production, and both triplet, everything. I want to get this done. Upon clicking this, are you able to see the screen and listen to that? I think there is a.
Sorry to interrupt, sir. Mr.
Sorry,
Jagannathan, your
Okay,
mic
okay.
is on.
Okay. So now this is the page giving the data.
Can you please unmute your mic, sir? Hello. Sir, can you please unmute your mic?
I unmuted now. Okay. So this data, this is actually XCOM data for the particular. I chosen a 74 as my atomic number. Now I'm going to actually submit the data in the web page. It is giving me the data for all the data what is available there. It is giving me the coherent scattering, incoherent scattering, photoelectric absorption, pair production in nuclear field, pair production in electron field, the total attenuation coefficients with coherent and without coherent. It gives me all the data. This data can be taken to any. We can take it and copy it to any database. We can keep it to anywhere as a text file or as a Excel sheet. We can use it. So I have already downloaded many of the things and I have it with me. So I'm going to show you how to use that also. That also I'll show you. Now you can have a download data can be given there. If I download the data, it is giving as a text file. This text file can be saved. This is how we have to use the XCOM file. Now this is what NIST data XCOM is here. Second important databases, the NIST is again E star, P star, and A star. This is another database available for stopping powers of electron, protons, and alpha particles. This is E star is for electron, P star is for proton, A star is for alpha particles. They have already tabulated the whole stopping powers, range, and other related quantities are already. It covers energies from 1 keV to 10 GeV. And this database is very much useful in EGSnrc because density correction factors are necessary. It is how it is uptight. If you go to this database again, here we can see that they have tabulated for many materials, not only for elements, they are also for other compounds also they have. Compound and mixtures, they also tabulated here. So many things can be done from here, like water, liquid, I can get all the stopping powers, radiative stopping powers. Then I can submit the data. I can submit it. Now it will give me a data table for all things. Stopping power it gives, collision radiative and total. CSTA range can be obtained from here. Addition yield and density effect parameter, that density correction factor we call that. That is also can be obtained here. So these two databases are very, very important. But of course, E star is necessary for basically for electron dealing. We will next time we'll deal with the electron actually interactions. That time it is very much necessary. For today's one, now we'll be talking about XCOM one. And third important, very important database, actually I used it very extensively in my lecture, and my work is also, that is EPICS 2023 electron photon interaction cross section. Electron photon interaction cross section. It gives me three databases. One is called EADL, atomic data library, EPDL, photon data library, EEDL, which is electron data library. These data libraries I used it in my work. That also I can show you that now here. This database, this is the web page for that. It gives me the, and these databases are available in two formats. One is called ENDF and ENDL. There are two formats available, and we can download the databases from here. This is a format. We can download it here from here. The database is available for individual materials and also for the whole material also it can get it. So each one gives you some information. So now going back again, so these three things I've been recommending that you should, every new beginner of this Monte Carlo system should go through these three websites. One is called XCOM website. This website is given here. Second is the E star, P star, A star website. That's also the second one. And third is this EPICS 2023 website. These three are very fundamental for going into physics part of the interactions, because all the data, whatever interaction coefficient, everything comes from here. Like I told you that EADL table gives you, because since I have already used EADL, EPDL and all very extensively here, so I'm telling that this EADL we get a lot of information. Suppose I want to know for a particular material, like for example 24, I have tungsten. For tungsten, I want to know what is the binding energy of every shell. I can get from here. What are the number of electrons from each shell? That also I can get it from here. So all the things can be get from this EADL database. On the other things also, radiation transition probability, non-radiation transition probability, that is also useful for us. Second is EPDL table. It gives you a lot of other data, in fact, coherent, incoherent, photoelectric by subshells. So that's also I'll show you the demo of this. These two databases I'll show you. Of course, I'll not deal with EEDL. EEDL gives you about the electron interactions. That will deal later. Okay. So as I told you that two things you have to keep it in mind, that the two important things are backbone for this any Monte Carlo system. One is the random number generators, other is the sampling methodology what we use. Now with the database available, that's the third part I can say, database available, because we can't generate all, we can't calculate it. We need to have all the data readily available so that we can move into the simulation part. So now I'm going into the simulation part. What is the basics necessary for the simulation part? Let us say, for example, I have a phantom where I want to simulate suppose, for example, I want to create a phantom. A three-dimensional one, where one photon is going to enter from this somewhere from here. Now how this will going to be counted for here, or the history of this photon is going to be counted here. That's what is everything to do with the simulation part. So we are going to start the simulation. So what is important is, in any simulation part, geometry, defining the geometry, material and cross sections, that forms the 50% of your work. So 50% of the work is done by at this level itself. If you are able to define the geometry clearly, properly to the any simulation software like GANT or EGSnrc, 50% of your work is over. So that's what is very important. So we have to define the geometry properly, how the geometry is going to be. Where it's going to be a simple phantom like this, or it's going to be irregular any other surfaces, or maybe you are going to have a geometry of multi-lift collimator. For example, let us say I'm going to model a head, linear head. It will have a blocks where the chamber is going to be there, where the target is going to be there, where is going to be your beam, the other defining devices, like we have a we have a scattering foil, we have a beam flattening filters. All those things can be modeled properly. Once you define this geometry into this one, then 50% of your work is done. Once you feed the geometry, next thing is now we have to go into the primary photons. How they're going to be there. What to be the photon? Whether what type of things we are going to. Whether I'm going to do a photon simulation, electron simulation, positron simulation, it could be anything. So first, next thing is I have to define the what is going to be a particle. Whether it's going to be a photon as a particle, I'm going to have an electron. Let us say today I'm going to deal with photon, so we'll deal with photon only. So when you have a photon, what I need is I need to have the energy first defined. What is the energy of the photon? What is my position? Position of the photon is given by x, y, z. Then what is the direction in which it enters? Third is direction. That is given by the direction cosines called ux, uy, and uz. So every photon has to have this information available, that is energy, position given by 3 coordinates, direction given by 3 cosines, ux, uy, z. So every photon contains 7 parameters. Every photon should, at any point of time, within the phantom or anywhere somewhere, should have these 7 parameters. So for example, let us say I have a photon here at any point here. So this photon should have the 7 parameters defined here. Only then I can properly, I can take the photon to which direction I want to take it, what is the energy, where it will have, what type of interaction it will, everything can be properly modeled. So for example, within a plane here, any one plane here, I have a millions of photons. There are so many millions of 10 millions, 100 millions of photons. So each photon should have these 7 parameters. Just for example, let us say, for example, 7 million of 7 million into 7 parameter. You can just imagine 1 million into 7 parameters. You have 7 million. So the data will be very huge, very, very huge. And that one is called your phase file. So the photons are defined at the any points here that have all the 7 parameters, and that I can put it in a phase, we call it a phase file. A phase file defines number of photons in that phase with all these parameters, 7 parameters. So normally phase files are having a very huge, it will be running in gigabytes. It will be maybe 1.1, 1.2, maybe 3 gigabytes. It's such a huge file. Normally the phase files are made of very huge database. They have so now, so we have a number of photons entering here. I have defined all these parameters. What is the energy? What is the position of the photon entering? What is the direction cosines? All things has been given. So once it enters here, the first thing I have to do is I have the photon at this level now. Now it's going to enter the phantom. Of course, initially the photon is alive now. Now it's going to enter now. I know that this what is the material made of? It may be a water phantom. It may be any other phantom. Let us say, for example, it is a water phantom now. It's made of water phantom here. So each material got its own attenuation coefficient. And first of all, we should know, as a physics student, we should know that the microscopic coefficient is, the microscopic actually interaction coefficient is sigma, which is called cross section. The microscopic level, it's called cross section. But at the macroscopic level, we have something called mu. This is called macroscopic level, we call it the coefficient. So first of all, we should be able to differentiate between the cross section. What is cross section? What is the coefficient? The cross section is per atom, whereas the coefficient is for the whole of the material. So I can say it's not exactly, it's a raw, otherwise I can raw similarity, I can say a similar is like a resistivity and resistance. Resistivity is for one unique material, and resistance is for a sample. Same way, cross section is for per atom, mu is. So mu is basically is equal to the number density into sigma. This is the actual formula. This is the actual basic fundamental formula. We should know that, because this is the cross section. The EPDL, EADL, EEDL files gives you the cross sections. From the cross section, we have to find out the mu. So that's the fundamental thing you have to understand now, because if somebody wants to work on EPDL, EADL, because that gives you the cross section, so some may be confused that why it's not giving the mu value directly. So we have to do this work actually internally. Okay. So here now, as the photon enters here now, the first thing is now I know based on my mu value, the photon may go without interaction up to a certain distance. That is called a mean free path. We call it as a mean free path. We call that as a mean free path. So a mean free path is the average distance a particle or a photon travels between the successive interactions or collisions. It means up to the distance of particular from starting from here, there is no interaction took place in this region now. There is no interaction from here to this point. This is the first interaction took place. So this distance is called mean free path. The mean free path normally given by the symbol lambda. It's coming from a formula called 1 by mu. It is basically, this is what actually defines the mean free path. We all know about that. But here, now I have to calculate the mean free path here at this level. Mean free path I have to calculate at this level to see whether how long the photon goes uninteracted. It goes here. So from that, I have to move the position, because let us say, for example, it started with I have to have an energy of 1 MeV, let us say. Position is equal to, let us say, 0, 0, 0. We have a direction. Again, let us say it is called 0, 0, 1, because it's going in the other direction. So it's going down here now. Now, how long it goes uninteracted, that I can calculate it by using mean free path methodology. I can use it. Once it comes here, then I have to do other things. Now, first we'll stop here. Now, I want to show you what is happening here. So, sample the mean free path. I have to sample it. In Monte Carlo technique, we have to sample the mean free path, because mean free path can be easily calculated. But when you have a number of photons, I have to sample it. Now, how to do that mean free path sampling, I want to show you. At the same time, I want to also tell you what is the importance of the number of histories. Why you have to go for a large number of histories. That also I'll show you the demo of that. I'll show you now. Okay. Now I'll go to the. I have developed some of the. In fact, I'm working on the Python for my Monte Carlo. I'm working on the Python. I use extensively. I used all the data tables. I used it. First of all, I want to show you one sample program I developed here. It is when here I'm going to mean free path sampler. It is. So I'm going to show you. I'm going to show you now the output of this one. I'm calculating for a 1 million maximum sample. I'm going to sample is 1 million. If I do a 1 million sampling, now I'll see that here you can see this. But what I mean free path I calculated theoretically is 11.67 of for energy of point. This is for 662. Sorry, this is for 662 keV. This photon is having 662 keV, for which I have a mu of photon is 0.086. I use this as a sample. I have used as an input. The maximum sample I'm using is 1 million. So you can see from this table, output table, what I intend to get is 11.627. If I use only number of histories or only 10 histories, let's for example, only 10 histories I use it. I don't want to go for large number of histories. I don't want to repeat this one again and again, sample it. So what I'm getting is, I have an error of 30%. What I'm getting, the value is 15. If I increase to 100 number of samples, I'm getting 9. You can see suddenly it decreases. I'm getting a value of 10. If I use 1000, I'm getting a value of 4.6% is the error, whereas I'm getting 11 point. For 10,000, 11.68. If I use 1 million here, I'm getting 11.627, which is 0.05. For example, let us say I want to do a higher one. I'm going for a 10 million. I'm going to do 10 million now. If I do it for 10 million, you can see from here, the error is now, it was earlier, the error was this much, okay, 0.05. Now it is reduced to 0.02. So the error is drastically reduced, relative errors. That's what I'm only saying, that I'm trying to say that is, it is better to go for a large number. So it is the probability one. It is always a large number. The theory of large numbers, that always law of large number matters here. It is always better to go for a large number of sampling methods. You should not restrict yourself to a low numbers. Low number leads to large number of errors. The variance or the errors is very, very high. So it is always better to go for a 1 million samples or 1 million histories or 10 million histories. So this is demonstrating that we have a large number of histories, gives you a more accurate results. So this is an example of a your mean free path sampling. Once once mean free path is sampled, then next is I have to go for the once the mean free path is sampled, the next thing I have to go for is the I have to move the photon now. I have to move the photon to the next level. It means that the photon has to move to the next level because I know I calculate, for example, let us say I calculate 11 centimeter is my mean free path. So within the phantom, I move the photon by 11 centimeters. Then I put a new position, a new direction, energy also I put it. So now the photon is moved here. The next, what should I do is now? So what the next point is now I move the photon here. I calculate, for example, I calculated this something to be here 11 centimeters. In this our example, it was 11.6 centimeters. So I move the photon to 11 centimeters. Now I check whether the boundary of the phantom is exceeded or not. I cross the boundary or not. If it is no, then I go to the next step. Okay. Now next step is sample the interaction time. The first step of sampling what we use is mean free path sampling, in which I need you can see this here, I generate a random number here. This is a random number. So what I do is I used a inverse transform sampling method. I used it here. So I generate a sample. I generate a one random number in the range of 0 to 1. Then check whether my calculated value is here or not. That I have to check it. So now I have to do is now I use this value minus logarithm of, so I have to do is minus logarithm of this epsilon value divided by the mu value. That will give me the x naught value. So this is my, likewise I have to do repeat this for n number of histories. That's how I calculated this mean free path. The next method is I have to go for the interaction time. Now once the photon has reached in a phantom, I reach this point here within the phantom. I reached one point here. I reached this point here now. This is the point here now. Now I have to first find out what type of interaction it has to undergo. So today we are discussing about the photon interactions. So we know about the 5 interactions of photon with matter. One is a coherent scattering. Second is incoherent scattering. Third is photoelectric effect. Fourth is our pair production. So there are 4 interactions I'll be dealing. Fifth interaction, photo disintegration, we will not dealing in now because that is not necessary for our material physics purposes. So I'll be dealing with 4 interactions. We'll be dealing in detail also. So we have to first see what type of interaction will take place. Either it is a coherent, incoherent, photoelectric, or pair production. These 4. Out of these 4, which interaction is more probable now? That we have to decide now. These 4 interactions, which is more probable? So how to find out now which is more probable now? Again, we have to take help of the random numbers and sample it to find out which interaction is more probable. For that, we have to use another methodology. We have to use another random number. This is the first random number we use here. Second random number I'm using it. I have to use the cumulative distribution function that I'll go using it now. I'll show you that also. Now what to do now? Sampling the interaction type. For sampling the interaction type, we have to use the cumulative probability density function or cumulative probability distributions, and I'll be using the acceptance rejection sampling method. We have to use it here. In this example, I'm using it here. We can use any other method also. For example, let us say I have already data available with me for a particular material, that is Z, maybe a 74 or 82 or 70, whatever may be, aluminium, lead, or maybe for water. I already have a data available from my database. I already have a mu value for photoelectric, mu value of coherent, mu value of incoherent, mu value of pair production. This can be obtained by the XCOM database also, I showed you now. So this data, by adding all this, I can get a mu total. Or mu total can directly, we can get it from database also, we can get whatever may be. So we have to get the individual mu values for every interaction type. The total also we have to get it. Now, how to do the CDF method? I told you we have to use the CDF method. The CDF method is, let us say I have a C1 value, it's equal to mu of photoelectric divided by mu of total. It means what is the proportion? What is the proportion of this is photoelectric in this total? That's called C1. So C2 is sum of this C1 plus proportion of the coherent with respect to total. C3 is C2 with again C2 plus proportion of incoherent with respect to total. And C4 is total, naturally, because the total will be total by total. So it will be that. Now I have the 4 values available: C1, C2, C3, C4. So I'm using the acceptance rejection method. So I'm saying that if for any random number between the 0 and 1, if the random number generated is less than C1, then I decide that the interaction should be a photoelectric method. If the random number generated is less than C2, it's a coherent method. It's a coherent. If the random number generator is less than C3, it's a incoherent. Otherwise, because naturally it is 1, it's called any of these conditions are not decided, naturally it will be for pair production. And this is the methodology used in EGSnrc also to get the interaction type. What interaction is going to happen? So this is going back here. So here sample the interaction type. That's what I discussed now. Here I'm using the acceptance rejection method, sampling method, to find out which of this interaction is going to probable here. Once I say this is the interaction type, then the physics part will come. That we're going to do now. Okay. So now up to this point, the Monte Carlo sampling methods and random number generators are being used. So here that's what I told you about. Okay. Hope up to this point it is clear. Anybody is having any doubt up to this point, is actually you can ask me now. Next we are going to different type of things. Any queries?
We can move on.
We can move on. Okay. So till now what we saw is how to get the data from the available databases, web-based databases available regarding all the interaction coefficients, E star values, all other data available from regarding the atomic level, photon level we have, plus how to sample. These are two important things. One is the mean free path. As far as photons are concerned, first we have to find out the mean free path, for which I have to use a random number generator, sample it. Second thing I have to do is the interaction type sampling. That means that we have to decide which type of interaction is going to happen, because we know the whole interaction is a stochastic process. We cannot decide by ourselves. So we have to use the random number generators. Okay. Now I'm going on to the physics part of the component of the interactions now. First thing we have to deal with is coherent scattering, and most of you must already studied. I'm not going to give you anything very important thing, very actually new things. Maybe some things are related to Monte Carlo, I'll tell you now. So when we talk about coherent scattering, it means that we are going to deal with both about the Thomson as well as Rayleigh scattering. There is a difference between the Thomson Rayleigh scattering. So in both this coherent, in the whole of the coherent scattering, the photon energy remains essentially unchanged. That means it's elastic scattering. There is no exchange of energy. There is no loss of energy. Only the photon direction changes. It means only the direction of the photon will be changed. So no energy change. And the photon and the atom will not get ionized, neither get ionized nor excited. Oh. This is very important in the low energy photon energy physics. In Thomson, so we have to differentiate between the Thomson scattering and the Rayleigh scattering. The Thomson scattering is normally valid for the energies less than, very, very less than the 511 keV. That means the rest mass energy of electron. So normally this is very, very low energies. So when we talk about Thomson scattering, we are dealing essentially with a free electron. It means we assume that the electron is mostly free. We know that the electron is having electrical field surrounding it. So when the photon interact with the free electron, only that photon, the electrical field of the electron will be interfering or interacting with the photon. It means, for example, let us say that I have a photon interacting with the electron. So the electron is having a own field here surrounding that. So this photon is going to interfere only with the electrical field here. So momentum is going to be exchanged here between this photon and the electron. There is a momentum exchange taking place here. So essentially only thing is that. So we can use the classical electromagnetic interaction methods can be used. So we can use these normal, just simple collision methods. Photon energy remains unchanged. The photon electrical field accelerates electrons. That's why I told you momentum get exchanged. The momentum of the photon is going to be interacting with the electrons. Electron oscillates momentarily at the photon frequency. The oscillating electron radiates energy. So what happens is this electron is going to radiate the energy, maybe in a different direction, can be anything. The electron is not going to get recoiled, or not going to come out of the shell, or it's not going to move at all. So only the photon changes the direction. That's the photon, that's the Thomson scattering. So when we discuss about the mathematical relationship of the differential cross section of the Thomson, I told you the sigma is the cross section. So d sigma by d, that means that d omega is the solid angle. This is solid angle because it can go into any 4 pi radians. That is something to do with the electron radius. Re is the electron radius. Okay, so Re square by 2 into 1 plus cos square theta. So it is essentially nothing to do with the either something to do with the Z or rho or any other parameters. So you can say that Thomson is not dependent on the atomic numbers and nothing to do with the density or any other things. It is something purely to do with the electron radius. And of course, angle dependency is there. Angle dependency is present always. So Thomson is a very simplest of the coherent scattering where nothing is going to happen. Only the photon is going to go in the forward direction or the backward direction. When you talk about the so let us first finish this. Okay, the total cross section is found to be the sigma t is found to be a constant. It's a constant, which is a fundamental constant. Classical scattering constant is this much. So it means Thomson cross section does not depend on Z or rho or any other material. It's basically constant. That's the reason Thomson cross section is mostly avoided when you discuss about interactions. This is a constant one, and more probably because Thomson cross section gives rise to only the forward and the backward scattering, not lateral scatterings. It's even. It's both the directions going to be even. You can see the angular distribution. It's going to be even. This is what actually generated from I'll show you my Python program also gives the same thing, sampling method. You can see it is almost the forward scattering and backward scattering is going to be even almost. It's going to be both sides, both are going same, both are even, and it's minimum near the 90. So it means lateral scattering is going to be minimum. Laterally is minimum, but forward and the backward is higher. It's a symmetric angular distributions. So Thomson has got a limitations because we know that this model deals with the individual free electrons, this model. So it is of no use to us because most of the time the electrons are always bound. So we deal with bound electrons only. So the Thomson model of the scattering or the coherent scattering method is not very much useful, and it is giving rise to a uniform scattering on both forward and backward directions. So it is of no use to us. Okay. Atomic charge distribution matters, of course. Interference effects are ignored because there is only the interferences between the one electron and the photon only. Now we have to go into Rayleigh theory. That's very important here for us. Rayleigh scattering method, here we are essentially dealing with the bound electrons. So Rayleigh scattering, coherent scattering assume that we have a bound electron. Actually, when you have an electron is bound to the atom, it is the other electrons which are in the atom also will be interfering in your scattering process. That's important. That you have to keep it in mind that other electrons will also interfere because the electrical field present with the other electron in the atom will also be participating in our scattering process. So this is a Rayleigh scattering is nothing but electric scattering by bound electrons. So the entire atom or the electrons of the atom participates in this scattering process. There's an interference between the electron occurs. So it means that one electrical field of one electron will interfere with the photon. Other electron will also interfere. So it means there's a mutual interference between the electrons of the atom with your photons. And the photon energy again, it's the elastic scattering. The photon energy gets unchanged when the direction changes. Bound electrons oscillate collectively, giving rise to a constructive interference modifies the intensity. So what we have seen up to this part is the Thomson scattering. The Rayleigh scattering, here we are multiplying by another term here, that's all. So it's a modified Thomson scattering, we can say. Rayleigh scattering is because here we are going to take care of the interference of other electrons in the atom. So that means that we have to put interference term here. So it is essentially a d sigma of Thomson by d omega into f square qz. That's the only modification here. That's what we are having here. Okay. So with this constant term, I'm going to have another term here interfering, and that is called the atomic form factor. The atomic form factors. The Q here is the momentum. Q is the momentum. It means that there is the interference. There is actually a modifier. Q is a momentum modifier, atomic number modifier, because the more number of electrons in the atom, so more interference will take place. So there is a variable here. So we have two variables interfering with the Thomson scattering. That's the modifier we put it here. And this data, atomic form factor data of all the basic elements are available in the EPDL table. The EPDL table gives you the atomic form factors from that one. We can extract from the table, we can parse that value and put it here. Okay. Now, at this moment, I want to give you one demo of how it is being achieved here. Okay. I want to do with the Python code I generated here. I have put my own code here. I generated my own code here. And here, I'm going to, again, run this code and show you how I'm going to sample the mean free path and also the interaction type. Okay, so we have all the 4 types available now. For example, let us say I'm going here now. Now you can see from here, I have done it for 10 times. Only 10 sampling I've done, nothing more. Okay, in 10 sampling, the first sampling, I get of course, this is for a material. This is a real material I taken, real data I taken from the XCOM and other things. For a lead, I taken 6 MeV as energy. As I told you that every photon should have these 7 parameters. So one is the energy, position, and direction. So 6 MeV. I can show it for both. I show it for 1 MeV also, other things also. Let us say first I will go for 1 MeV. First I'll show for 1 MeV. Okay. So first I'm going for 1 MeV. So this is for 6 MeV. First I'll show you that. I'll go for the other one. Now here, in the first sampling, I got a mean free path of 52, which is actually very high because 6 MeV. Okay. Now, is this 1 MeV? Sorry. Now you can see that it was starting with the position 0, 0, 0. Now it moved to new position X, Y, Z. The interaction type sampled is Compton. Next, I've gone to actually a Second sampling, it's giving a mean free path of 45, new position, again Compton method. Third is because it is random sampling, so we have a photoelectric method. Second is photoelectric, Compton, photoelectric. You can see this from here. Now I'm going to a 6 MeV. Okay, for this is for 6 MeV. You can see this pair production because it was 1 MeV. Pair production is not at all there. Now pair production is also probable now. So we can see from here again the mean free path sample, new position has been calculated, and your interaction type is also sampled. We can get a lot of pair productions there now. Nowadays we have pair production more increased. So this is I showed you the two steps here. Both the steps I showed you now. Okay. Now we have to go to rally sampling now. What is a rally? Here, of course, since the system will go a little slow, I taken the actual value of FQ values from the EDPL, EPDL, and the FQ squared is calculated here now. Now I'm generating a graph. It takes a little longer time to show you the graphs. That graph is showing this is a Rayleigh scattering. The probability, you can see the graph is like this. And this is the Thompson scattering. I showed you the same graph by my Python graph. By Python method also showing the same type of. This is sample. These are sample values. This is the actual value, analytical value. These dots are actually showing the sample method. Sample is also almost going near that one. So that is also there. This is the. This will come little later. SQ value. SQ is a scattering component, and this is the FQ value. One is the FQ square value, the SQ square value. Now, so what happens is now what we saw was the one is the Thompson scattering, but when in reality Thompson scattering is of no use to us, so we'll be going for Rayleigh scattering. For Rayleigh scattering, what we need is the atomic form factor. These are available in the EPTL table. We can take it. This is the same graph I showed you. We can generate this also. We can see that. So the dependence on atomic number, of course, there is a dependence on atomic number because that's what we saw that there's a FQ. This value is there. Dependent on atomic number is already there. Rayleigh scattering roughly scales as Z squared. It is found to be strong in high Z materials. The higher atomic number material is very high. Rayleigh scattering is high. Weak in low atomic number materials, and coherent scattering decreases with the energy as the energy increases. But low photon energy, it is dominant. Compton scattering dominates at high energies because as you go higher, incoherent scattering decreases and incoherent scattering increases. The comparison between these two is this is the free electron model. Compton is a simple angular sampling because nothing is necessary, no Z value, no other actual thing. We have to simply use the theta value and we can just sample it, but that is giving rise to a very constant value always. Whereas Rayleigh scattering, it is a bound electron model. Rayleigh includes atomic form factors. Rayleigh has a stronger Z dependence. That means Z square. It is high square, Z square dependence. And we need to have a form factor data from the EPDL table or XCOM values. This is the same thing summarized in a slide. This is again the same thing in a different slide. Is showing that how the initial photon interact with the individual atom and that radiates energy. Okay, this is Thompson scattering. Whereas the Rayleigh scattering, because all the electrons are participating in this, the whole incoming photon is interacting with all the electrons, means that they are coherently means they are having actually oscillating and radiating energy, and they merge together, gives rise to a single photon in a direction. That's about coherent scattering. So when anybody wants to deal after interaction type, suppose I find out that coherent scattering is there in that sampling method, then I have to use the Rayleigh scattering method. So I have to get this value from the form factors values, multiply that and get the values and find out because what is happening is now once we decide that there's a coherent scattering taking place, now I have to find out what the angle in which it is being scattered. So I have to use the Rayleigh scattering, the angular dependence value, the formula. From that, I have to find out what angle it's scattered, then move the photon to that direction and place it there. Next is incoherent scattering. We call it as a Compton scattering. interaction between a photon and atomic electron, where photon changes the direction as well as the energy because it's a inelastic process. Energy transfer to electrons, atom get ionized and excited. The Compton normally dominates above 330 keV and up to 10 MeV, where then we have other processes dominating. So the process is a gamma photon or X-ray photon interacting with the electron, giving rise to a scattered photon and also the recoil electron. The photon approaches the atom, interaction with the weakly bound electron. Remember that again, we have two models for Compton again. We have a free electron model and also have a bound electron model. So many of the EGSnrc and any other MC code uses a bound Compton. We have to account for bound Compton. That's why they say bound Compton. Specifically, they say that. A free electron model, again, Compton is very easy. But a bound Compton model, we need additional factors. The interaction with the weakly bound electron, energy is transferred to the electron, and the electron goes in a different direction, phi direction, that's another angle. Photon, the scattered photon exits with a lower energy in a different direction, theta. Okay. Electron will deal later. So because electrons are, we have to treat them as a other free electron approximation, we can do it. We can say that the photon electron is free, stationary, isolated. Then we get a very simple model of your Compton scattering. But when you have a free electron, what we mean by is now the binding energy of the electron is very, very low compared to the incoming photon energy. That's why we call it a free electron. So this is this free electron theory is given by the Klein-Nishina model theory. Already we have seen about this r squared by 2 values and all. We have seen that this one little bit modified one. So it is same thing. We can see that one. These things are coming almost same, constant. What you are seeing here, what is seen in Thomson, is basically they are coming in the same. So here is the Thomson one. We have a Raleigh, and it is modified to a Klein-Nishina model. That's all. It's a Klein-Nishina model. It's almost same. This is why basically this is what is used in Monte Carlo methods. Klein-Nishina model theory is very commonly used there. Okay. So this is a scattered photon. What is the energy? We can calculate from using this Klein-Nishina model. The shift in the wavelength can be calculated from here, from this formula. The incoming photon interacting with a free electron and ejecting an electron, recoil electron, and the photon, scattered photon goes in with a less energy, goes in a different direction. But what happens is, I'm not going to deal with this mathematical part. We know, everybody must have studied about this, how it is coming. But what is the essentially for Monte Carlo I'm doing here? Bound electron effects. As I told you, that Klein-Nishina model is talking about the free electron model. That means that there is no interference of other electrons in this interaction type. But we are dealing with when you deal with the whole atom, we have so many other electrons are there. What will be interference of this electron with the interacting electron? So we have a real electron process consists of binding energy and initial momentum. What happens is when the electron interacting with the when a photon interacting with the electron, let us say we have a free electron, but this could be a part of a one shell. There may be other electrons in the shell. There are other shells containing electrons. Relatively, there are other shells containing. This may be a free electron. We can say because the binding energy of the outer shell is very low. Okay, the electron can go into one direction. This electron, the photon go in another directions. H nu dash. But what will be the interference of this electron when it is interacting here? What will be interference this? That's what gives the bound electron effects. When they are actually interacting here, there is the energy broadening is taking place. Doppler broadening, we call it a Doppler broadening. What happens is because of these interferences between the other electrons, the energy spectrum of the scattered photon get broadened. It's not essentially a single photon, it gets a broadened energy. And that depends on the shell dependence, which shell we are interacting, whether it's dealing with the N shell, O shell, P shell, or maybe with the L shell, could be anything. So it depends on the shell, the broadening is different. Okay, so that's what I'm going to talk about here. So we have this is coming from the Klein-Nishina model. This one, this is the one, this one. Now I'm going to multiply this another factor here. Like this is SQ, I can say, sorry, this is SQZ. Again, I say SQZ. Okay. So same thing as the FQZ, same thing as the FQZ. FQZ is used in coherent scattering. SQZ is used in this data is called scattering function. That's called atomic form factor. This is called atomic form factor. This is called scattering function. This is also coming from EPDL again. This is also coming from EPDL and EADL. So this value I have to multiply it because there is a dependency of the momentum transfer. Q is momentum transfer and the dependency on the atomic number of electrons because Z number of electrons. So this accounts for atomic binding and the binding energy. That means how much interference or how much momentum it can transfer, and the electron momentum distributions. Because of the bound electron momentum, it broadens the scattered photon energy. So the h nu dash is being broadened. And this is very essentially very important when you are talking about the PET, and other detectors like we have a gamma camera detectors and other detectors, how much broadening taking place. These are very essential for nuclear medicine people also. Okay. So scattering function, this is called scattering function, has to be multiplied. This data is available here again. So essentially what we do is we calculate the clinician theory function, multiply by this value, we get this cross section. So incoherent scattering cross section is coming from this function. So Monte Carlo, when you say that we need to have a bound Compton, then it calculates this value. Again, the recoil for electron, that will be later on, that not today's lecture. The recoil electron carries kinetic energy. That what happens to that, how the electron going there, how the photoelectric electron going, all these things will be dealing with in separate lectures. Next is photoelectric absorption. So we know it's called photoelectric absorption process. So essentially, the interaction photon dies out. It is totally absorbed in the atom itself. A photon is completely absorbed by an atomic electron. The incident photon interacts with the bound electron. Photon energy completely absorbed. Electron gets ejected. Now the important question remains here is where it interacts, in which shell it interacts. Is it interacting with the K shell, L shell, M shell, or which shell it goes? That's the question remains here now. We all know that photoelectric absorption deals with the interaction of photon with the bound shell electrons, and we know all the electrons are bound to the shell having binding energy. So now the question comes, in which shell it interacts? There is no data available. How to do it now? Again, we are using, that's the reason we have Monte Carlo uses sampling method here. The sampling method finds out, like we found out using sampling method, we found out which type of interaction occurs. Same here also using sampling method, we have to find out in which shell it interacts more probable, which shell is having more probability. That we have to find out. So we use a Monte Carlo method to find out. Let us say, for example, the interaction taking place in K shell. The K shell electron is ejected out. There is a vacancy occurring in the K shell. The vacancy is produced in the K shell. What happens to the atom? The atom has to relax because the atom is now in an excited state, ionized state, because there is one electron missing in the shell. It has to come back to ground state. The atom has to relax. So when a K shell vacancy is there, how it will relax? Whether the L shell will fall down, the M shell will fall down, which shell will fall down? Again, that question remains now, and that whole process is called atomic relaxation process. Atomic relaxation process gives you the idea, gives you how it's going to fill the K shell now, because we said the example is K shell. So main process is gamma or X-ray photon interacting with an atom, releasing a photoelectron, and ionized atom is now going through a atomic relaxation cascade process. The photoelectric effect dominates at low photon energies. Essentially the cross section of photoelectric cross section is proportional to Z power n, where n varies between 4 and 5, divided by E cube. So Z is power of 4 to 5, it's almost 4 to 5. and divided by E of 3 to 4, it says. This is what actually many textbooks say that it's very. We can get the data from the EPDL table also, EADL table, EPDL table we can get. There's a strong dependence on atomic number because E power 4, Z power 4, atomic energy also is strong dependence. The interaction occurs K shell, L shell, M shell. Binding energy determines whether interaction can occur or not. Because now the interacting photon, the energy is low than the binding energy of the particular shell. What we have sampled here, the energy of the binding energy of the shell, what we have sampled is lower than the photon energy, then it's probable. If the binding energy is higher than the incoming photon energy, then it is not probable. Then we have to sample it again and find the other probabilities. So we have to remove that probability from that. We have to remove that. The photon energy must exceed shell binding energy. And we know about the absorption edges. Normally we have a KH, LH and thing. That is also useful because there is a sharp drop in the spectrum. What we get from the attenuation coefficient, we get it, or from the cross sections, we get it. There's a sharp drop because what happens as the energy increases, the coefficient keep decreasing up to a particular point. Then suddenly it increases to this point. It goes from here. Again, it starts from here. Maybe just example, I'm telling that it goes from here. So there is the edge effect. This is called edge effect, and this is also accounted for in Monte Carlo modeling. And what is the energy of the photoelectron emitted? The photoelectron emitted is having energy. The energy of the photoelectron is, or we can say energy of the photoelectron is equal to the energy of the photon minus the binding energy of the shell in which it interacts. So once we know, I showed you that EADL table contains binding energy, that we can get the data from EADL table. So I minus that energy of the photon from that one. Okay, from this one, I get the what is the energy of the photoelectron. That we can find out. So this is how the Monte Carlo proceeds. I'm just giving the examples of Monte Carlo wherever it is necessary. Okay, that we can get. So what we have to do is now in Monte Carlo for photoelectric, sample the shell in which it interacts, either it's a K shell, L shell, M shell, and whatever may be the shell, and generate the photoelectron. Then simulate the atomic relaxation process. That means that how this shell is being filled up. That's called atomic relaxation, we call it. Okay. So again, we have to use a sampling method. The shell is filled using a sampling method. Okay. We use a cumulative probability distribution. Again, CDE or CP cumulative probability or CDF is being used. Before that, I want you to actually, we know that most of the people we know, actually everybody knows that when you say about interaction taking place, K shell, L shell, M shell, anything can happen. We also should keep it in mind that K shell is having only one subshell. L is having can have a maximum of 3 subshells. M can have a 5 subshells. N can have a 7, 9, and other shells are having 9, 11, 13, and goes on. It means that each shell is made of a subshells. Each shell is made of a subshells. So we have to keep this in mind that every shell has got a decided number of electrons, but it can be residing within any of the subshells. It can be in a L1, L2, L3, M1, M2, M3, M4, M5. It can be anything. It can be anything. So that is, we have to keep that in mind that it can be in a normally the electrons are present in the subshells. So we have a shells, we have a subshells. That's called we have a family of shells. Keep that in mind. We have to keep that in mind now. Okay. Now, so how the atomic relaxation can occur now? So the vacancy is filling of a particular shell. Let us say K shell is being vacancy is there in a photoelectric process. It can be filled by the higher level shells. It can be L shell like L1, L2, L2, L3. It could be from M shells, M1, M2, M3, M4, M5. It could be from anything. Likewise, it can be anything. Now, the L shell vacancy can be filled from any of the shells here. Any of the shells. It's completely probability. during the process of the filling of the shells. Let us say simple. We'll say, for example, let us say K shell vacancy is going to be filled by a L shell. The difference in the binding energy of the shell will be emitted as a photon, and that we call as a characteristic exchange. Everybody knows about it. During this filling, let us say, for example, L shell filling the K shell, the excess energy need not be always emitted as a photon. It can be emitted as an electron from the another shell. So, for example, let us say K shell while filling the K shell from the L shell, M shell electron can be emitted. M shell electron can be emitted. So, K shell vacancy filled by the L shell, but M shell electron is being emitted, and that electron emitted is we call as Auger electrons. Auger. It's called Auger electrons. That means that the excess energy present in the atom, it emitted as an electron from another shell of the atom. That's called Auger electrons. This is the difference between the shell binding energies. It's not that always. One of the relaxation processes characteristic X-ray emission. One of the relaxation processes characteristic X-ray emission. There are other emission processes like Auger electron process. There's also other type of emission relaxation process called caustochronic and supercaustochronic. It may be sometimes that, let us say, for example, I have L1 cell vacancy is there. It's filled by L2 shell. L2 shell is falling down to L1 shell, filling it up. Because of that, maybe M shell electron is emitted. And this is called caustochronic. It means the transition, electron transition should take place within the subshells of the atom. And other electron from any other shell can be emitted, and that's called caustochronic. This is a special case of Auger electrons. There's also supercaustochronic, in which, let us say, for example, I have a L1 shell vacancy filled by L2 shell falling down, and because of that, L3 electron is being emitted. It means all the three are from the same family, and that is called supercaustochronic. Anything is possible. So it means that we have Auger electrons emission. We have caustochronic, in which the transition takes place within the same family, but electron emission can be taking place from any other shell. Supercaustochronic is all the three shells involved are from the same family. So we have a characteristic X-ray emission, and also we have Auger electron emissions. These both are the methods of relaxation, atomic relaxations. One is emitting a gamma photon, X-ray photon, or any photon is emitted. One is emitting electrons. So this photon emitted here has to be separately dealt now in our MC code. Electrons will deal later. Okay. So at this point I want to show you in one of my Python code. I have taken the data from the actual data from the EPDL data. I have taken the data from the EADL parser. I have taken it now here. This program calculates parses the data, EADL data, and it gives you the what type of is available. Okay, this is giving the binding energy of the different shells of a particular atom. I can find out. I can get this data from these any atom I want. I can get from this code. I have taken it for the this is lead. This is the binding energy of that one. Then I'll show you the. I have another code here. Actually, now you can see from this code now. Okay, now here it's giving what type of transition, photoelectric atomic transition can take place. Now this first sampling, it gives it is actually from the EADL table, EPADL table. What happens is it emits X-rays. What's the probability? What is the energy of the X-ray emitted? If it's Auger electron, it finds out whether it's a costochronic or supercostochronic, because it has to find out from the which shell is involved. So this way I can find out from the data from the EADL, EPDL table, I can find out what type of emission is possible, atomic relaxation taking place, whether it's giving rise to a photon emission or giving rise to a electron emission. If it's the electron emission, whether it's the Auger electron, costochronic or supercostochronic, that I can find out from here. Okay. Okay. Now, actually, I'll go a little fast and move on to the next one. Yes, photoelectric pair production. This is actually where not very much. Actually, I'll not go detail in this one. We know about that. Pair production is dealing with more than 1.02 TeV. There are two things possible. One is the interaction with the nuclear field. So that gives us a pair production. Two charged particles are emitted, and there is also a pair production with the electronic field, we call that. Otherwise, a pair with electronic field, pair with the nuclear field gives you two particles. This gives us three particles, triplet production. Okay. And what is exactly needed for our Monte Carlo here is very important is Bethe-Hitler formula. That is what is being used in the EGSnrc code, other codes also. Differential cross section can be obtained using a BH formula, Bethe-Hitler, and this cross section is proportional to your tire production. Tire production is the cross section is proportional to z squared, atomic number square of the atomic number. Triplet production depends on the atomic number, not square of that one. And low photoelectric, higher Compton, and a very high energy, more than 1.02 to pair production taking place. And applications, we actually this is not necessary very much. So now here, what is Monte Carlo method for this PP for pair production? Once we sample the type of interaction, when we find it is a pair production. Now what we need is what is the sample energy sharing between the electron and the, now first of all, what we have to find out at this point, once we decide is the pair production, then what will be the energy what is the energy sharing between the your electron and the positron, both energy sharing. So once we find out the energy sharing, how much energy each will be sharing, because we know the photon will die out, photon will not come out, only the two particles will come out, and we have found out what the energy sharing. Next thing what we have to do is sample the angles, in what angle they will be going, what direction they will be going. Once we decide this, then these two particles should be separately dealt in the particle transport. That will deal in the next classes. That is using the Bethe-Hitler formula, how to calculate, how to sample for electrons, how to sample for positrons, what will be the stopping powers, how to calculate using that will deal with it. So here up to this point, what we will be doing is now is sample the energy. Once we decide it's a PP, then what we will be doing is now we will be dealing with the what the energy sharing, what the angle. After this, now it will be totally a particle interactions. It is totally particle interaction that will be dealing in the next sessions. Now I'll be dealing for one example. I'll deal today now, just another 5 minutes. Every code requires I'll be dealing with EGSnrc, not any other code. So otherwise, every EGSnrc code requires a minimum of 2 files. One is input file, which a user will give it. That is both the files we have to give it, of course. One is physics parameters we will be dealing, that we have to input. Other file deals with the material data file. What type of material it is, what is the constants, that means what is the interaction coefficients, cross sections, that is the one. Okay. And so I'll be going directly into the now that's the last slide. In fact, I'll be going to the now one example I'm going to give it is using the EGSnrc. Today I'll be dealing with the simplest of EGSnrc code, that is called dose RZ. It's called dose RZ. That's the simplest of all models of EGSnrc. Because this is RZ, it deals with a cylindrical geometry. We have a cylinder having many slabs. This is the interface, what we get once you launch EGSnrc RZ, dose RZ. It is giving a interface like this. This is a GUI interface. in this GU interface. With this, we'll see later. The very important thing is general. We have to see. I had told you there are two important things we need. One is called the input file. This is the input file. This is the material data file. Material data file is called PEX file. We call it a PEX file in EGSnrc. So this is the input file. This is the PEX file. So this deals with the geometry, source, and every other things. This deals with the material data. What exactly material consists of? What are the dosimetry parameters? Like example, I told you about your mu values, cross sections, and any other data we need, we can give it. Is it what is the density correction factor? Is it a mixture, compound, or a simple element? We can deal everything in this. For today's, I taken the default example. It already available in this called those are the NRC template EGS input. Okay. And we can create our own. That I think that will be beyond the scope of this today's lecture. I'm going to deal with this. I'm going to tell you how to run this program and tell you. The first is general. This is what is there. Second is input output control. Nothing much to touch here. That is out of this one. And again, Monte Carlo. As I told you, Monte Carlo needs a large number of sampling meters, large number of histories to be dealt because so that we get the accuracies. So if we go for a low number of histories, the accuracy or the errors what we get will be high. Errors will be very high, accuracy will be lower. So normally we go here. We have gone here. I taken a 1 million histories. Sorry, 100,000 histories. I can increase to. So for the simple example, I'll go for 10,000 histories first. So the time of running will be less. Okay. Next is geometry. Here we are simple geometry is given here. One of the geometry here, as I told you, those are just deals with the cylindrical geometry. It means we have a cylinder made of many slabs. Let us say, for example, I have a circular slabs stacked one over another. Example is here. One of the example is I have a 10 slabs. Each is made of 1 centimeter thickness. 50 slabs, each is having 2 centimeter thicknesses. I'll show you the how they are constructed. Here we have another file called preview RZ. It's another GUI, separate GUI in the EGSnrc, which is used to visualize. Now we can visualize it. We can visualize the geometry. Okay, I'll show it a little higher one resolution so that it will be easy. I have magnified it. That's all. The simplest geometry is called. Just imagine that this is a cross section of the cylinders. This is a cross section of cylinders. These are slabs. These are slabs. The horizontal ones are slabs. The vertical ones are the circular cylinder. So 10 slabs are made of 1 centimeter here. 50 slabs made of 2 centimeter each. It goes up to 100. So it means that I have a total 60 slabs here, 50 plus 10. I have a 10 slab here, 50 slabs. So it's totally 60 slabs. One is having 1 centimeter, is having 2 centimeters. And I have a radius. First one is 1 centimeter radius. Second is up to 2 centimeters radius. Then I have a 5 centimeter up to 5 centimeter radius. Then I have a 10 centimeter radius. Then a 100 centimeter radius. So this is the one. I can change it. We can change it to whatever you need. You can do it. I can simply, for example, let us say, suppose I want you want to see that one. I'm changing it now. For example, let us say instead of 50, I'm going to make all the thickness are going to be 1 centimeter only. I'm changing it to 1. So I have a 10 slab made of 1 centimeter. Again, I have 50 slabs made of another 1 centimeters. I'm going to save it. I'm going to visualize it now. You can see this. All are made of equal thicknesses. So user has got a. That's why I told you that geometry defining is the main part of any EGSnrc, actually Monte Carlo code. Once you define the geometry, once you visualize the geometry properly, then half of your job is done. Okay. That it should be like this, no problem. But I want to have a different type of radiuses. That also you can make it. I can have a different radiuses here. I can make it. Why you want to make a radius? Because here I'm defining that all the
Sorry to interrupt, sir. We'll have 5 more minutes.
Yeah,
Let's.
I'm going to wind up now. I'm going to wind up now.
Yes, yes.
Okay. So here we have all the things are made of water. I'm introducing a small volume of air cavity within this now. I have small air cavity introduced in this now. Okay, that's what I visualize it now. I'm going to the next one called source can be defined by giving a different type of actually source available. I can go to any. You can see the label is changing here. We can go. I'm going sticking with the first one. We can change the incident particle as a photon, proton, or electron. Then transport parameter. This is important. All the today's lecture, most of the things we dealt here is being given here. Whether what type of sampling I'm going to use it, whether I'm going to use a simple sampling or Cosmos. This is the KM sampling. We call it a Cosmos sampling for interaction of electrons. And here also Bremsler angular sampling. Here also we have sampling methods. So we can have many sampling methods available in this code. So we have to define. I told you that data. We also have a EPDL data. EPDL data. We have PEX4 data. So we can have a choice to give any data you want. We can have it. Okay. And there are other things, transport parameters, they given it, the plot controls. Okay. Now let us say I'm finished with this one. I'm going to save it. Save it. Now I'm going to execute this. When I run it, what is happening? We see this. It is running for every radius, every material there. And now it is giving rise to interactive run is completed now, and it is giving no errors are found, and it is giving a output for each and everything, how much time it took place. And in my library, in my folder, in this file, there are other files are being created, and which gives rise to a dose, and every cylinder and every radius is we can calculate. We can calculate that dose is being displayed there. That also we can do it. I think that we have to deal separately. But here I just want to showed you that I showed you that how the transport parameters are useful here, what type of thing, how to choose this thing, what type of choice you have. E cut, P cut, everything we'll deal later. It's atomic relaxations, whether you want atomic relaxations, a simple relaxation you want. I told you just simple atomic relaxation. You suppose you want to reduce the time of time of the run of the particular code. I can say off, so time will be less. And that's the reason I should know first what I'm doing here. So once you know the physics behind this, I can easily control this. I can control this. Okay, so I can say that now I almost completed now. Thank you so much for the actually I completed the part one photon interaction. Thank you so much for patient listening. Any doubts you can ask me.
Hello, doctor.
Yeah.
Just I want to ask you about Tobas, which is using the Genta 4 from the Monte Carlo.
Okay, you are using Topaz.
Tobas, yeah. I have a
Okay.
project to do in the Tobas regarding to the radiotherapy.
Okay.
Okay. For the coordinate, if I want to keep it the origin 000 XYZ,
Yeah.
how can identify the program that coordinate it should be in some area? I mean, if I wanted to keep it in the target or in the end phantom.
Okay. Okay. What you asked actually it is equally applicable to all EGSnrc also. What you asked the question is the thing is suppose I say that I'm going to keep it at 000. Okay. We have to first define the phantom. Whether I should have a minus x plus x, minus y plus y, and then z. If I want to say that, suppose I have this, let us say for example, I have phantom starting from minus 5 to plus 5 x-axis. If I say I have a y-axis from starting from minus 5 to plus 5, but the z is starting from 0 to z, then invariably my 000 is lying at the center of the top of the phantom. But you say 000 simply, it means it is going at the one corner of the phantom. So when you define your geometry, first of all, you have to define that what type of geometry it's going to. Either it's going to be have a negative coordinate also, positive on both x, y, and z, Or if it's going to have a phantom starting from 0 to x, 0 to y, then your 0, 0, 0 will be at one corner of the phantom. That's the mistake normally we do. So first you have to visualize what phantom, what type of thing you are going to have, what type of phantom you are going to have, or what you are going to visualize, what you are going to simulate. Accordingly, you place your coordinates that way. So once you say that I have a minus x, minus y plus y, then 0 to z, then I know my 0, 0, 0 coordinate is going to be at the center of the top of that one. So my photon is going to enter from the top at the center, exactly at the center. Then it's going to interact with the other materials. And I can put any phantom here, I can put any slab there, that we can do it. So that first of all, you have to visualize it and see how the phantom is going to be.
Okay, doctor, thank you.
Mr. Obaid, you can unmute and speak. Ask your question, sorry.
She's also asked.
Doctor?
Yeah.
If there is any recommended AI, we can use it for the coding using the tubas.
Okay. Actually, basically, I have not done anything with the Topaz. Okay, I have done with the EGSnrc only, and actually, I'm developing my own Python-based code. In fact, I'm in the process of making creating a small code, which can, I don't know whether how robust it will be, how fast it will be, but I'm just developing because that's the way of learning the things also. So I have used all EGSnrc. I never done anything with Topaz.
Sir, there is one question in chat box, sir.
That is for students interested in radiation transport. Is it GANT4?
Yeah, GANT4.
Is that one?
What the foundation?
Okay.
Yes, sir, that one.
Again, GANT4, actually, see, the basic foundational topics for physics topics remains the same, irrespective of whether you use EGSnrc, GAN4, Topaz, or any other type of actually Monte Carlo codes. As I told you that each code has got its own type of actually coding methodology, how you input the data. But one thing is sure that you have to input, the user has to input the data. So we need an input file and we have to define the material file. That's going to be same. So how we are going to define each code, how it defines it, we have to go through the basically the how they are having the code actually. We have to go through the what type of documentation they have. But the physics remains the same, irrespective of whatever code they use it. So first of all, I will say that the users should always have a fundamental actually clarity about the physics being done and how, because only then we can find out whether we are doing any mistakes in the geometry feeding or in physics calculations, which methodology they are using, which algorithm they are using it. So we should have a basic knowledge about that, irrespective of whatever code you're using, because everybody will not. I have not used GNT. In fact, I tried to install it. I used it initially, but somehow I think I could not. I'm not actually. I'm not an expert at GNT, but I installed it. In fact, I used it for some time. EGSnrc and GNT. EGSnrc I thoroughly installed. I have been using it for so many years. But GNT I installed initially, but I could not actually go through beyond this one. But I feel that students should especially concentrate on the physics background, physics, what is the essential physics, how the data is being tabulated, how the data is available in the network. I told you about the sources of data, that I see that, and the algorithms, sampling methodologies. I feel that students should concentrate on these things. So if there is no more question, we can.
Yes, sir, we can wind up. And thank you, everyone, for your active participation up to till into the Q&A session. Uh, Thank you, sir. We sincerely
Thank you so
thank
much.
Dr. Bilal
Thank you.
Hussain, sir.
Thank
Sir,
you. Thank you so
then
much.
Thank you.
Hope I think I
Wonderful
put
session.
some input, something actually physics, the basic background I given you. That's what I
Yes.
fundamentally I thought that actually that because we may be going into higher level Monte Carlo things, but the foundational basic physics should be known. How the Monte
Yes.
Carlo is handling the physics. That's my actually idea of
So,
giving this today's session.
yes.
Thank you so much for everybody for patiently listening.
Thank
Thank you.
you. Thank you.
Thank you so much.